continuity of multivalued function. But it's just fancy names. I'll just explain. I mean, in full generality, it is a fancy thing, maybe, but we're just doing a simple version of it. Let's take an example. Let me give an example. I'll just take an example which I know works. I know that every example should work, but let's take this particular one. Okay. So let's take this polynomial pz. So first we are taking this polynomial. I'll just call it pw for a certain reason. W. And this is 3 times w to the power 5. And we have 25w cube plus 60w minus z. So basically this z is also a variable. Okay. But I mean, for every fixed z, we are defining this. I mean, so this is a function, right? This is a function. It's nice, everything good, no problem. But from here, I want to define a new kind of function. And that is, so think about this. Think about this. For every z, pzw has 5, so not maybe distinct, but 5 roots. Right? You put z equal to 1, you put z equal to 2, you'll get 5 roots, 5 different roots. It will depend on z. As you change the z, you get different roots. Okay. Now, if you look at this association, where you have for each z, you go to roots of pzw. Z, and here we'll put the roots at z of this polynomial. Yeah. So what are we saying? For every point, let's say 0 is the input. This will go to potentially, it will go to 5 points. Because they will not lie on a polynomial. This is a complicated thing, right? So, I mean, if I do it for a polygon, if I do it for a roots of unity, this question will become trivial. So, I don't want to do like that. There's no point doing like that. Won't learn the technique. This will involve a lot of interesting things about modulus you have to use and whatnot. You see, so every point has 5 images. They may not be distinct. Sometimes it will be 4, but a generic point will have 5 images. Okay. So is this so far? Is it okay with everyone? Right. That for some z, the polynomial will have distinct roots, and for some other z, it may not have all distinct roots. Okay. Any questions? Then there's a question, homework. This is a simple question. This will not be needed here, but it's a very simple question. Find all z. So I don't want the roots and all. You can't find the roots. You can't find the roots of this. Okay? At least you can't solve for them. Find all z for which and there will be finitely many of them, and that's a good thing, for which PZW has non-distinct roots. It's not a very hard question. You may think, oh, it's complex. How will I use derivatives? Think. The derivative in polynomials is used formally. You can use it in complex numbers. You can use it in modulo P also. Okay. So try to figure out the Z for which this will not have distinct roots. Okay. You have to do some thinking. If I don't know how much you know polynomials, it will depend. So think, and we'll discuss this next time. But coming back to this question, we have this association, right, where Z goes to roots of Z, and this is like a 1 to 5 thing. So if you look at it, if you look at this association naively from C to C, this is not the right way to look at it. But at the beginning, this is how you will look at it, right? C to C. Then this is not a function. It is not a function. One point is going to many points. Okay? So that's why it's a multivalued function. It's not really a function. So it should be a multivalued hyphen because it's not a function. Yeah, the other way around is may not be a function. Yeah, that also may not be a function. But that what you're asking is a very deep question. For which such multifunctions is the other way around also a function is a very deep question. I don't know how to, but I know it's a very deep question. So it depends on something called branches. If this function has one branch, then the other way around will be, and so, but later. So the other way around may not be a function because, as you understand, for some other point also, the polynomial may have the same root. But for irreducible, yeah, it can have. Oh, no. Ah. No. It's not a very difficult question for this case. Think. Let's think. So the question that Adish is asking, I was also thinking about this, but I was thinking in the wrong way earlier. I was not thinking for this example. I was thinking for this thing generally, which is not, we don't need to think. But this example is the right place. So if you look at this, so I'm just going to what Adish is asking. I'll come back to what I was saying later. I mean, just after this. So first of all, it's clear to everyone this is an association. It's not a function. Okay, not a function. Is the other way around a function? First, let's just think. Okay, let me not clarify this or anything because you can think independently first. So this is one too many, but is the other way around one too many, or is it? It can be many to one. Right. And not more than 1 point in the range. I mean, so we are okay with the other way around being a partial function, but we don't actually need that. We just, okay, let's just keep it like this. It's the other way around a function. Basically, just focus on this. Can there be two different values of z which give the same root? We'll forget about the surjectivity and then so on later, right? Because this one-to-many has to be surjective for the other way around to be a full function. We'll think about that. First, think about this. So the question basically is, can there be a z1 such that w0 is a root here, but w0 is also a root of for some other. So the same w0 is a root. Yes, yeah. So in that way, it's good, but it would be good if it's also because then it would be from C, right? That's a different question. It's not difficult. It is not. I don't know. It's not difficult. We have actually already done it. Surjectivity of polynomials and so on. Okay. We have actually already done it, but you can finish it later. I will state it clearly, but you can do it on your own. But let's answer this. Can there be another Z2? Can there be a different Z1 and Z2? You can see it pictorially, which have a common root. Common root is the word, right? Mm. No, for this particular polynomial. Yes. For this. Yes. Yes. So you can see. Yes. Right. So if you just put it, it's just trivial, right? But you can also basically see that that these two polynomials are actually co-prime. Pz1 and Pz2 are co-prime, and which you can apply this kind of ideas later if here also it was a variable, maybe z square plus 1 or whatnot. Here also you could you understand, try to extend the thing. But yeah, this case is completely clear. So yeah, so this is a very special thing. Right? It basically means that for every point there are these things. So ZW factor. Yes, but that itself will not be enough. Like if it was a Z square, then this would not be true. Right. If it was a Z square here, then the reverse may not be a function. Then you would need two complex planes in the range to make it a function. Yeah. So but let's complete this. So here we have, so there was a, I think, good question. It's simple. It's all about just writing it clearly, but that's what most things are about. See, so this we have to cut, and you get, sorry, so Z2. So it's not possible, but it's not possible for us. So see, all of us should appreciate this, that it's not possible for a very specific reason. It is not like a universal thing. Okay. It's not possible because of a very special thing, that this is Z only. Yeah. So now I will just, but since I have written that this association is from C to C, then this question is not yet solved. So prove that it is, because you have to show surjectivity and so on, right? I mean, as an association from C to C is the reverse of function, is not yet solved because you have to show surjectivity, which you can easily do. I'll leave that. Okay, but do it because, yeah, otherwise. So note it down. Now, basically, we want to now actually this kind of investigation also makes us more comfortable with this scenario. So there is one point going to several points. Okay. Now we want to define a notion of continuity in this case. Okay. How would continuity of a usual function be? If you have a point here and it goes somewhere here, then what does continuity mean? Continuity means that by changing the values of the domain small enough, you can make small enough changes in the values of the range. But that basically means that you can take, that basically means that for given any epsilon neighborhood here, now it becomes an actual neighborhood. Yeah. So this is epsilon neighborhood, just epsilon. Given any epsilon neighborhood around the image point, there exists a delta neighborhood. You don't know, it's can be very small, may need to be very small, right? So this is the delta ball, and this is the epsilon ball. So given epsilon ball, there exists a delta ball. This is basically the definition of continuity, right? We all know this. Delta ball such that f, if for the single valued function, f such that f of b delta is inside. Everybody's okay with this? This is the definition of continuity. This should be the definition of continuity for a single valued. But nobody needs to say that this is continuity. One can just say things like this and ask the question. Okay. In this case, actually, we can say it in a more algebra looking way. Okay. But it's just a question. Let's see. So this is the definition of continuity. What would it become in our situation? What should it become? So in our situation, it would be just the analogous, right? We just want to, but it's not even it's not a function. Okay. But we are still trying to make sense of the same thing. We are trying to say that given one branch of Z1, given one possible image of the association, not the function. So earlier I said function, not function. Given one image of the point Z1 under its association under this relation, let's say this is W1, and these are all like W1 prime, these are different. I mean, in fact, under some change of coordinates, you can relate them, but those are some very drastic change of coordinates. Right now, when we think of change of coordinates, we think shifting and so on. But change of coordinates could also be like applying some sort of a flow to the whole plane. Like there are points, and it's like just throwing maybe a wind passing through this. Then everything kind of just changes, not in translated or whatever, but they change in a good way. And that you can take as new coordinates. So those kind of coordinate systems changes have to be done to. So those are the more natural things that happen, right? Which we are knowingly or unknowingly modeling. But the point is, coming back to this, as you expect it to be, we are saying that given any neighborhood, let's say epsilon neighborhood, okay, there exists a delta neighborhood. So I'll just here. Yes, there exists a delta. So delta neighborhood. So given this, so you know that PZ1 of W1 is 0. Okay, so W1 is a root of, they can just say like this. W1, you don't need to say a multivalued or whatever, right? W1 is a root of Z1. Given a ball around W1 like this, show that there is a ball around Z1. Z1 is not as the origin, I'm just on it like that. Given there, so there is a ball, some ball around Z1, such that now I cannot say that this maps to this, right? Because it does not. It maps to all sorts of places. It's not a function. So I cannot ask for that even, right? It's impossible. But you know what I'll ask, right? I will say that for every point in this neighborhood, at least something maps in this, right? Such that for all Z prime in this thing, okay, there exists a W prime in that ball, okay, such that P of such that at Z prime, at least one root is W prime. So at least one root is pretty close to the original root. So when you move Z1 a little bit by Z1 plus minus epsilon up to distance, then the roots also don't move so much. Well, at least one root does not. I mean, the other roots also don't move, but they're already away. So the root that we're considering. It's a pretty believable thing, right? But how do you prove it? So first of all, is it believable? If we change the coefficients a little bit, how much can, if you change the product of the roots a little bit, how much can the actual root, at least something should not change too much, right? If the product is not changing too much. But how do you prove it? Is the question. So this balls and all, you can just write all this, right? W minus, Z prime minus, basically this language will never be given, right? It will be like Z prime minus Z1 is less than, delta, and right, you understand. How do we do this? This is the question. So try to absorb it first, then we will try to give some hints. We'll not finish it completely, but yeah, that will be homework, but we will try to get to a place so that we know the idea. Mm-hmm. Yes, that's the definition, right? Exactly. That's right. That is the definition. Right. So if you want to change the roots a little bit, then you want to show that you can achieve that by changing the inputs a little bit. And the intuition is that if you change Z a little bit, right? So if Z minus Z1 goes to 0, right? If you change Z1, Z a little bit, which means the product is not changing too much. So if the product of the roots is not changing too much, then how can all the roots, I mean, if the product is not changing too much, then at least one root must not change too much. It must not move too much apart. For Z1, the roots of Z1. At least one root of Z1 should be close to W1. You want to fix a delta or epsilon. No. For any epsilon. See, you first of all see the epsilon will be given to you, right? So let's see then. So yes, that's what we always fix, right? Because we always claim that small changes in the domain will create small changes in the range. So to prove our claim, we have to fix a small change in the range and show our claim. Yes, yeah, exactly. Given this, you have to. So the epsilon is fixed, and how do we? Mm-hmm. Okay, you want to do that? Yeah, okay, that's right. But that is not very consistent with the balls, because this is a very weak inequality. It's true, but is it useful? Say some root of Z1 is epsilon close to W1. See, this is what we want to show, right? That as Z1 approaches Z, some root of
Z1 should approach W1, kind of. Some root should be there. So if we take smaller and smaller balls around Z1, then at least some root should end up, some root corresponding to that Z1 should end up in the ball. Right, okay, right. So okay. Basically, this is also consistent with the notion of continuity, right? But if we try to translate it from what we have said initially, is we want to show that around W1, you take any ball, you can find a small enough ball around around the pre-image around Z1, such that that ball around Z1, for every point in that ball around Z1, if one of its roots will be inside the epsilon ball, right? You can find a small enough. Yes, exactly, right. That's what it is. Yeah. So to translate, last thing, yeah, exactly. Yeah. So to translate that, what it means is that if you take a small enough, no, so this is not Z1. Yeah. What I'm saying is, if you take Z1 and take it closer and closer to Z, right? When Z1 approaches closer and closer to Z, and after some point, when Z1 is close enough to Z, that is, when Z1 is in that delta ball, right? When Z1 is close enough to Z, then at least, when Z1 is close enough, then at least some root of Z1, some image of Z1 will be inside this epsilon ball, which means epsilon close to the to W1. So that is what I've written. So the Z1 means when Z1, as Z1 approaches Z, which means that, at after some point, right, when it is delta close. So finding such a delta such that every Z1 inside that delta, one image is inside epsilon ball, is the same thing as saying that when Z1 goes closer and closer to Z, then some root of Z1 becomes epsilon closer to W1. It is the same thing. So just see if I could explain it well enough. So is this okay to everyone? Mm-hmm. 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 Okay, so but okay, but this is the real number, right? Substituting this in the polynomial. Right. Okay. For some Z, you'll be able to find. You'll be able to find some Z, kind of. So let's see. So if you put this, yeah, at this point Z is not fixed. If you put this, yeah, so this is close to W1, and then you want a Z1, then you want a Z for which this is 0. Right. To that Z to Z naught. Yeah, right. So this is confusing. Yeah, that's the problem. Yes, that was the confusing, right? Yeah. So yeah, anyways, this is Z naught. Should be Z naught. Yeah, but yeah, you can find it, but how do you find it? Yeah, I think you can find it, right? So, no, the problem is that, see, you had W1 was a root, mod W1 is not a root, right? So, I don't see I think it's a very vague way, but it's very unclear. Okay, you see a problem. Okay, then yes, exactly, because complex numbers are so varied, they have all the directions. Right. Yeah, something like that. Yes. Yeah, maybe it can be. Yes, but yeah, but for that, see, for that you have to. Yes, we just in the ball, but you see, for that you should try to put not mod W1 but W1. You put W1 plus epsilon and then expand it using binomial theorem and whatnot, right? And then you will get a condition on Z, because W1 is a root of Z when it is Z naught, right? For W1, right? And then if you put, but it will get really messy, I think. Yeah. Hmm? I'll say epsilon. Yeah, yeah. Yes, right. Right. I mean, the every. Right. Yeah. Yes. Yes, yes, yeah. I mean, in fact, every point in this ball will look like this only, right? W1 plus epsilon for some small epsilon. I mean, you understand, it will not be the same epsilon, but kind of some epsilon prime. Yeah. Yes, that's right. I mean, that's how it is. When you approach W1 arbitrarily, it will look like this. That's good enough. And then from here, you can figure out the condition on Z by using the fact that it condition on Z with relation with Z naught. You see, when you put it in expand, right? The part of W1, you can put that to be 0, right? Or it will be equal to Z naught. And then you'll get the remaining part with a lot of epsilons. And then you'll get, so when you expand this, right, you will get a part which will be like this, and then there'll be a part which is full of epsilons, right? Epsilon primes, and then there is a part which will be, then there will this only be z, right? And then from here, using the epsilons are, I mean, in terms of the epsilons and in terms of this, in terms of the epsilons, you can find a condition on the distance between z and z naught, right? Z and z naught will be equal to some epsilons, epsilon square with some constants, and some w1 will also be there, but there are some, bounded distance and so on. So you can bound the mod of this, right? You can say that the mod of this, and you can make this mod, right? And then you will get. It's a vague idea, not very precise, but you can make it precise. Okay, so basically we get our delta roughly. Yes, we get a condition on z with respect to z naught, that z should be this close, and you can, hopefully your process will be reversible. That is important. Okay, if it's only one base implication, then also you are gone. So if at each step it will be like this is, this follows from the next one. It should be like that. But you have to do, then you will get, hopefully. Okay, so that is the thing. I mean, the idea is that when you are close to W1, then you can find some Z which is close to Z naught. Okay, then the Z will be close to Z naught. And that we are basically putting values in it, but this is a bad way to do, and I'm not even sure it will succeed. Okay. There is a better way that will use the theory, which is basically the basic theory, that is factorization. Factorization, right? Theory of factorizations can be used. Basically, if you use your intuition, you will kind of feel that this delta should be epsilon to the power 5, or there'll be relation with the degree. Okay, but it's hard to maybe see it now, but you can, what I'm trying to say is, if you use a factorize, basically if the reason because we're not using the factorization, then this PZW1 thing that was coming in the expansion is coming, but there's a lot of additive things. Okay, but there's a unique feature about polynomials that every root has this multiplicative factor, right? That's a unique feature about single variable polynomials. That's very unique. It's not a geometric thing, right? That it leads to a factorization. It has geometric consequence, but it's an algebraic thing. It's not algebraic. It's an arithmetic thing, right? That there's a division that you can do, a division algorithm. Right? It's a completely, hardcore arithmetic that is there. So that we are not using, and that is a game changer, because till now it's like this polynomial is a very geometric thing, but it also has. So what I'm saying is that basically, yeah, so if you extrapolate from it, that basically we're trying to show that you can take epsilon. So, I mean, yeah, as Z1 goes close to Z naught, some root will move close to W1, right? But let's keep it simple, okay? Let's say that, let's try to explore this, okay? If all roots, so if all roots of PZ are far, so if Z is such, it's not PZ, I mean, add Z, okay, are far from W1. What do I mean? I mean that if PZ is, we can use a factorization. If PZ is of this form, W1Z, W2Z, W3Z, 4Z, If all the roots are far, then you can write this. If this is the situation, and if this z is bad, if this z is such that none of the roots are close to w1, which means w minus wyz is, this is the meaning of far for us, right? It's more than epsilon distance from w1. So this is wrong from w1. From w1, they are all far. Then what can we say? Then yeah, can we say anything? So this will imply that pz of w1, right, mod of this is more than epsilon to the power 5. Now you can finish it. I will not say anything. Okay. If needed, review the thing. Okay, on your own, you can see, or you can try to think about the things on your own and see if needed. But just take 5 minutes, not to answer this rest of the question. If you know it, it's good. But the whole picture also. The whole picture. Hmm. 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 Okay. Yes, because I think after some point, the problems are usually not calculate. Means the spirit of the problems is more like analysis. So they actually are simply, maybe that might be wrong. Huh? Hmm. Yeah. Yeah, they can be, but the spirit is not elementary, right? Means the language is not elementary. The elementary language is not the right language for it. So that's why it looks difficult, right? So the solution to that is obviously just to keep trying. And when you see the solution, or when you discuss the solution, when you come across something which is non-elementary, which can be used to solve it, just take it with you as your tool, obviously with the understanding and so on. What else can you do? This is what it is. I mean, that's why I try to do these kind of questions, which are, okay, these questions are maybe slightly more theoretical, but they're also elementary. But I don't know what to say, but yeah. So you have to pick the tools, non-elementary tools along the way. Hmm? In the element. Yes, yes, because that ingenuity which you see, it might be real ingenuity, and it is in any case, but it is an unwrapping of the non-elementary language, right? That it is practice, but see, when you see a very long solution, it's usually the motivation, or the real thing lies in a good language and a short solution. but because the language is used is non-elementary, so the solution becomes big. And people who do it, they maybe engineers, or maybe they know the non-elementary side of it, and they kind of simplify it and write it, and they can, right? Especially in official solutions, that's always the case, because people who make the problem, they make it from their own high level maths, and they write it in elementary language, and they like, this is an example of that. This problem, okay, this is not that ingenious or anything, but it comes from some theory, but then it is simplified, and I'm asking. Okay, it is like that. Okay, so is everybody okay with this? Okay, if there are any questions with this also, please ask. Is there a class on Tuesday? There will be, because now I think, yeah, now I'm more free. I will take. So yeah, so it's already very late, so I'll not say anything more. I've given some other problems along the way today. Try them, try to finish this, and then we'll continue next time. Okay. Next time we will not do, we'll go into more of integration. Okay then, thank you. Thank you, bye. It's already very